Hello everybody and welcome to chapter 6.5. Today we're finishing exponential and logarithmic functions, or chapter 6 as I should say. So today we're once again going to try and make connections, but today we're mostly focusing on logarithmic scales in the physical sciences. So we're first of all going to learn what the different logarithmic scales are and then how to apply them in different ways. So let's do that. So in this chapter, we will learn about different logarithmic scales which provide a convenient method of comparing values that typically have a very large range. So for example, if we were dealing with numbers between 1 and 1 million, it would be much easier for us to use a logarithmic scale rather than a linear one. So what do I mean by that? Instead of going by 1 plus 10, so 1, 11, 21, all the way to 1 million, it would be much easier for us to use a base of 10. So we go from 1 to 10 to 100 to 1000 to 10,000 to 100,000 to a million. As you can see, we only had 6 different steps there instead of around 100,000 if we're going by 10 linearly. There are 3 scales that we need to learn for this chapter that are perfectly logarithmic scales. Those are the pH scale, the Richter scale, and the sound intensity scale. However, we will also discuss 2 exponential functions, which are the exponential growth and decay function, as well as compound interest. The reason why these 2 are included is because they still may require us to use logarithms to solve them. Plus, it's something you will still have to learn within the textbook. For example, I think in chapter 7.5. So I thought it would be much easier for us to cover them right now rather than later on. So over here, I actually wrote out all of the scales and their respective equations. So take a look at that. Once you feel like you have them memorized, which you will have to have them memorized, we can start discussing the application of each one. So our first one is the pH scale, given by the equation the pH is equals to the negative logarithm of the hydrogen ion concentration. That is what this H plus means. So again, I'm going to describe that here. In chemistry, the relationship between the pH and the hydrogen ion concentration is given by this formula here, where H plus is the concentration of hydrogen ions in moles per liter, which we write as the following. So we can use this equation to solve several questions. Here I've listed 3 of the most basic ones you might be asked. So the first one is calculate the pH of if the concentration of hydrogen ions is 0.00001, so 4 zeros after the decimal point, moles per liter. So the solution for this is really easy. We don't know what the pH is, so we let that be, but we substitute in our value for H plus. Then we take log of 0.00001, which is -5. Remember, when we don't have a number at the bottom, that means it's a common logarithm of base 10. So then we got -5. -5 times -1 is equals to 5. Therefore, our pH is 5. For our next question, we're given that the pH of vinegar is 3. It's asking us to calculate the hydrogen ion concentration. So, given our formula, we can write this in exponential form, right? So this is base 10, so we're at 10. Then we know that our pH, we could divide this by -1. So this would become -1. So we have a power of -1. And H plus is what our equals to. Then we substitute in the 3 for our pH, and we get 10 to the power of -3 is equals to H plus. So then 0.01 is equals to H plus, and so our answer is 0.01 moles per liter. Again, pretty simple. You could probably do this yourself with no problem. The last one is a little bit more complicated, as you can see by this beautiful long explanation, but don't worry, we'll get through it. So, if the hydrogen ion concentration is a measure of the strength of an acid, I don't know why it's written in gibberish, let's fix that, of an acid, how much stronger is an acid with the pH of 0.6 than an acid with a pH of 3.1? Well, let's see what we know. At first, of course, we know our formulas. So our formula, we just transformed it into an exponential function, and this is what we got. First, we substituted in 0.6 for hydrogen 1. This is how I'm marking our first acid. So 10 to the power of negative 0.6, you could put this into your calculator and you find out that that is equals to 0.2511. We could also do that same procedure for 3.1, or 3.2 I should say. I think this was 3.2. And then we substitute that in. We get 0 followed by 3063095 for hydrogen 2, which would be our second acid. Then, since we're talking about how much stronger the first acid is compared to the second one, we're actually taking the ratio between those two. And so we get H1 divided by H2. Again, we put those numbers in there and we get that our answer is approximately 398.1 times stronger. Now, if you understand this, you should be good to go with the pH scale. Now, let's talk about the Richter scale. So, the Richter scale is given by the formula of M is equals to log of I divided by I null. What the scale is used to do, it is used to measure the earthquake's magnitude and intensity. So for example, if we were to try and measure an earthquake, where it is given by this formula here, I would be the intensity of the earthquake being measured, and I null is the intensity of a standard low-level earthquake. So that might sound a little bit confusing, but do not worry, it will be fine. So the important thing here is for you to understand that this over here is a ratio. It is the comparison between a intensity level of one between the intensity level of another. Then, however much that intensity differs, we take the log of that and we get our magnitude. So for example, we have this question here. If the average earthquake measures 4.5 on the Richter scale, how much more intense is an earthquake that measures 9? So there's two ways to do this. First of all, you would take your substitute 4.5 into an equation like this, then 9, and then you subtract one from another and solve. However, when you do that, you have to deal with log of 1 divided or minus log of another value, and so those we haven't learned yet. So this is why we have to find out this formula here. Finding this formula here we will do in chapter 7.3 when we actually learn the quotient law, so do not worry too much about it, but you have to memorize this formula as well. Once you know this formula, your life becomes so much easier. So again, we're just going to substitute the values in. So 9 minus 4.5 is equals to log of your your second earthquake divided by the intensity of the first earthquake. And so we get 4.5 is equals to log of those values. Rewriting this in the exponential form, we get 10 to the power of 4.5 is equals to the relationship that the two values have, and then 10 to the power of 4.5 is 31,622. Therefore, the earthquake that measures 9 on the Richter scale is 31,622 times stronger than the earthquake that measures 4.5. With that being said, that is as difficult as these questions will get, so let's move to the next one. Sound intensity. So this here is measuring in decibels, which is these wonderful bee looking things over here. So what this means is the following. The difference in sound levels, which is measured in decibels as I just said, can be found using the following equation. So the decibels of one sound minus the decibel levels of another sound is equals to 10 times log of the relationship between their sound intensities. I is also measured in watts per square meter, just in case you're wondering how to write that in an answer. So again, when you're dealing with sound intensity, you will have to have a table like this, because this table here will give you the values of the sound intensities, the decibels for each kind of sound. So if your question, for example, like this one, was asking you for the sound of a jet engine compared to normal city traffic, we would look at the graph, identify where the jet engine is, which is 160, identify where the normal city traffic decibels are, which is around 85, and then we would substitute that into our equation. So let's do that. Substituting these values in, we get 160 minus 85 is equals to 10 times log of the ratios. So then 160 minus 85 is 75. 75 divided by 10 is 7.5, and then we have log of the ratios again. Rewriting this over here in exponential form, we get 10 to the power 7.5 is equals to the ratios. And so 10 to the power 7.5 is 31,622,776. Therefore, our answer is that the sound of a jet engine is around 32 million more times intense than the sound of normal city traffic. Next, let's talk about exponential growth and decay. Exponential growth and decay is extremely useful when it comes to predicting the outcome of certain scenarios. So the function is shown as this: f of x is equals to a times b to the power of x divided by h. Each of these parts have their own meaning. So f of x is the final amount or number, a is the initial amount or number, x is the number of growth or decay, h is the growing or decaying period, and then for exponential growth, b is equals to 1 plus the growth rate, and for exponential decay, b is equals to 1 minus the decay rate. So for example, if you were told that you have a half-life or a doubling life of something, that would imply what the b value is. So if it's a half, we would take half of 1, which would be 1 over 2. If it was double, that would be 2 times 1, or 1 plus 1, which would be 2. So you have to keep in mind those wordings for any type of word problem. With that being the case, we can now talk about an example of growth or decay. So here we have an element, iodine 131, and it has a half-life of 8 days. You personally have 24 milligrams of iodine to begin with. First, we need to determine the equation that represents the amount of iodine 131 you have after t days. So we need to identify what we know about the function. Well, we know the initial amount, so a is 24. We know that we have x or h as our growing or decay period, because we have a half-life, we also know that b has to equal to 1/2. We don't know what t is, but t is responsible for the time, and so our answer would be f of x, or f of t, I should say. Let's put that back. F of t is equals to 24 times 1/2t over 8. This should also be 8 or 16, since that is exactly what we're inputting in. There we go. Again, for that question, we just inputted what we knew from the initial statement. For B, or for the second job point, we're asked how much iodine will be left after 16 days. So T, again, is the same as our X value, and so we just substitute that into our equation. So F of 16 is equals to 24 times 1/2 to the power of 16 over 8. First, we'll deal with the 16 over 8, which is equals to 2. Then we do 1/2 squared, which is 1/4. Then finally 1/4 times 24 is the same as dividing 24 by 4, which will give us the answer of 6. Remember, our initial or our final answer should have the same units as our initial amount or number, which was in milligrams. Therefore, our answer is that there will be 6 milligrams of iodine 131 left after 16 days. Lastly, let's talk about compound interest. So compound interest is given by the formula over here. And you should have already familiarized yourself with this concept in grade 11 during your small finance unit. If you don't remember it, these are the 5 parts of the compound interest formula. So A is your future amount, P is your present value or your principal value, R is the annual nominal interest rate, so it is genuinely how much interest you'll be getting as a decimal per year. The important part is as a decimal. You cannot have it expressed as a percent. N is the number of times the interest is compounded per unit T, and in case you're wondering what T is the time this procedure goes on for in years. So using these 5 attributes, we can solve the following question below. If $4,000 is to be invested at 7% per year, which is compounded semi-annually, in how many years will the investment be worth $9,800? Well, let's identify what we know. We know that our initial value or present value was $4,000. We know that our interest rate is 7% per year. So 7% in decimal form would be 0.07. Then it is compounded semi-annually. Semi-annually means that it is compounded 2 times a year. Therefore, our time or our N value would be 2. We do not know what T is, but we know that A, our future amount, is equals to 9,800. So this question, we are solving for one unknown, and that is T. So first of all, let's input all of the values we just discussed into our equation. And B will get 9,800 is equals to 4,000 times 1 plus 0.07 divided by 2, all to the power of 2t. So first, what I would do is divide both sides by 4,000, which would get us 2.45 is equals to 1 plus 0.035. In case you're wondering where the 0.035 came from, that is just the value of 0.07 divided by 2. I was trying to save as much space as possible for this question. That is why I didn't include that explanation there. Next, I just added 1 and 0.035 together, in the brackets, and so we got this equation here. Now, just for you to understand, we can easily apply the square first with the value we already know, because when it comes to the power rules, the power rule states that this over here is the same as the first power times the second power, which is 2t. So there is not really any problems with us doing that. So again, when we take the square of 1.035, we get this long number here. This form you should be familiar with. This is our exponential form, which we know we can solve for using logarithms. So let's write in a logarithmic form, and we will get log of this base of x, which is 2.45, is equals to t. So now, if you have a calculator that can accept a base, you could input this into a calculator and solve, or you can use the change of base formula that we discussed yesterday to input these two values into your calculator. Again, remember that your b value will go to the denominator and your x value will go to your numerator. And so either way that you do this, you should get t is equals to approximately 13.02. However, as you can see, my final answer is 13.5 years. The reason for that is because we were asked when will the investment be worth 9.8k. Well, if we were to round this down, it would be below $9,800, and so we have to round up to the next compounded period, which would be half a year later, which would be 0.5 months later, or 0.5 of a year later. Hence, our answer is 13.5 years. With that being said, today's class is done. That is all we had to learn for the remainder of chapter 6.5. So today I've assigned all of question 1 to a C and 6 to 11. All of these questions should be really straightforward, as we've discussed most examples and ways to do them already. Again, this is the reason why I will not be showing you how to solve those questions explicitly. Overall, I hope you really enjoyed chapter 6. Next time we'll be starting chapter 7, which is still a continuation of exponential and logarithmic functions, but it's a lot more algebraically based. So I'm hoping that I will see you then. If not, again, I hope you had a lot of fun learning today, and thank you for listening. Bye bye.